Okay, today we're going to take a quick look at metric prefixes. These can be the difference between a successful mission and a failure. So if we're flying a drone and we have a data representation of the height of that drone or altitude of that drone, and we have a failure to communicate the appropriate prefix, perhaps that drone smashes into the ground instead of landing neatly. So these can really change the way that we perceive success and failure in the field. So on our agenda for this video, we'll look at why we use them, very intuitive explanation of that. We'll take a look at the two types of notation that use them, which is positional and engineering. Scientific is included because engineering notation is a type of scientific notation, and positional notation is the sort of notation you're used to using when you go to the grocery store. So the sort of things that you see in your daily activities. And then we'll take a look at how to convert between them with two examples. So why prefix? Well, the metric prefix system, or the engineering notation, is a very concise, very minimalistic data representation for magnitude and precision. So if we notice here, I have a statement that says 5.0 milliamps. This decimal 0 infers a precision of 1 decimal place, and this milli infers the magnitude. So we can see that this is much easier to read than this. And when we get into even smaller numbers or much larger numbers, we can see that we're quite thankful to have this type of representation instead of this type. So over here we have positional representation. This is positional notation. This is engineering notation. So definitely prefer the engineering notation over the positional because it helps us prevent errors. So that's essentially why we use it. And of course, if I have implied precision like 5.000, this is okay. This is very easy, right? To say that I have 3 decimal places of precision, positional precision. Positional precision. Sorry about that tongue twister. If this was 5,000 instead, well, suddenly there's a room for error that is generated. If I print this off on a schematic and I send it somewhere, perhaps I get some oil or flux or I don't know, solder on it and damages the number, and I end up with a miscommunication. So we generally want to use the best possible notation, and that would be something that is concise, and that would be engineering notation. So let's take a look at the differences between scientific notation and engineering notation. Well, immediately we see that the way that precision is inferred is a little bit different. So in this case we have 3 positions of precision, or 3 decimal places of precision, and in this case we have only 2. But they both do an excellent job at communicating precision, and they both do an excellent job at communicating magnitude. However, there is a little bit of overhead with the scientific notation, and it's not quite as compact, so it's going to be much more difficult to print numbers like this onto wires or components. So people in the field would prefer to read a number like this because they do not have to spend any time moving this position around. So that's one of the major reasons or major differences between these two types of notation. But we're going to take a look at the table of metric prefixes and note that the other major difference is that there are actually increments of 3 in the power of metric prefixes. So scientific notation, which can be 10 to the 0, 10 to the 1, 10 to the 2, and so on, is going to be a little bit different in the power than the metric prefix, which is only in intervals of 3, or increments of 3. So keep that in mind when writing numbers in engineering notation. At first that can be a little bit tricky. And we have things like kilo, which we're probably used to seeing, like the kilometer per hour. If we're working with computers, we're probably used to seeing terabytes and gigabytes. Perhaps if we're working with electronics, we're used to seeing picofarads and femtofarads. So certainly many examples of this system in use in modern science. So over here we have the symbols, and there are more metric prefixes than these. These are just the most popular ones. With a cursory search, you can find many publications of much larger numbers than this. And the beauty of tables like this is it helps you ensure that your numbers are correct, right? You have a quick reference guide for factors and a quick reference guide for powers and names. So it's always good to check against a table like this when you're starting out. So now that we have those tools, let's take a look at a very quick example. And this one's going to seem trivial, and that's because it sort of is. So step 1, convert to base units, right? Given a packet size of 1 kilobit and a data rate of 5 megabits per second, what's the transmission time? Well, let's get that in base units and then go from there. So in base units, we have 1,000 bits and 5 million bits per second. So our transmission time becomes the packet size divided by the data rate. And of course, with notations like this, it becomes very easy to do the computation. That's where scientific notation triumphs. So we do the computation, and over here we see something important. We don't want to say 0.2 milliseconds. With engineering notation, we always want the first number to be non-zero. So we would much rather have 200 microseconds than 0.2 milliseconds. And now here's where the communication triumphs, right? Scientific notation is excellent for computations, but engineering notation is excellent for communication of results. So keep that in mind when using these number systems or notation systems. And now you're probably saying, well, yes, this example was actually quite trivial. What about something a little bit more difficult? So let's take a look at one where we'll have a little bit of dimensional analysis before we solve the problem. If a car is driving at 100 kilometers per hour for 10 seconds, then how many meters has it traveled? Good sip of coffee. So the first thing we want to do is get base units. So we want this in meters per second. So here we have 100 kilometers per hour. And if I want to convert kilometers to meters, I know that there are 1,000 meters for every 1 kilometer. And now if I want to convert hours to seconds, I know there is 1 hour for every 3,600 seconds. And using dimensional analysis, I'm able to divide out the units I do not want. A kilometer divided by a kilometer is just 1. An hour being divided by an hour is just 1. And I'm left with units of meters per second. So I multiply this and divide by this, and I have my speed in meters per second, which is very close to 28 meters per second. And at this point, the solution becomes quite trivial. The distance the car has traveled, 28 meters per second, multiplied by 10 seconds. Considering the dimensional analysis, we have a second dividing a second. And we see that we're left with meters. So the car has traveled 280 meters. So here we've done both metric conversion as well as unitary conversion, unit conversion. So we can see the power of these metric prefixes in quickly and easily communicating information, and quickly and easily communicating information here at the end results. So hopefully this has helped you understand a little bit how metric prefixes work and helped you gain an understanding to be able to use it in your future tasks and future assignments. So thank you for taking the time to listen to my tutorial. I hope it helps you. If you found it helpful, please like this video and subscribe, because there will be many, many more helpful tutorials. And until next time, I bid you farewell.